Hello everyone. Today we're going to talk about biasing a transistor. Basically, we need to put the base junction at a spot where when you apply a small voltage to the base, it produces a base current, which in turn turns on and off the transistor, which reduces the collector emitter effective resistance and therefore controls that current. Last week we introduced this characteristic curve graph, which graphs the collector current here on the vertical axis with the collector emitter voltage on the horizontal axis. And then also we have our base currents here going across to the right. So for each base current, we have a corresponding collector current and a collector emitter voltage. This is a family of curves. It's called a characteristic family, transistor characteristic family of curves. And I like this graph, and I like the next one we'll look at very much because, first of all, it shows this load line. It's called the load line. And this Q point here is sort of the transistor's happy place. This is where it wants to operate. This is the quiescent, Q stands for quiescent operating point of the transistor. That's when, theoretically, in an amplifier, nothing's happening. It's no signal. It's silence, if you will, for an audio amplifier. And as you apply base current, the microphone, for example, is feeding current to the base, this curve, or this line, goes up and down. So you travel up the line this way to the left and higher when the base current goes to 400 microamps here, in this case, and when it drops down to 200 microamps, you go to the right and lower, and therefore the corresponding collector current is less. Notice the amplification here. We're going from 200 microamps to 400 microamps on the base, and the collector is going from 20 milliamps, this is, to 40 milliamps. Okay? Now what's the beta of this transistor? Okay, the beta of this transistor is going to be, in this case, any one of these you can use. It could be 40 milliamps divided by 400 microamps. Okay, so that's 100. Also, which is worth noting on here, is the VCE, the collector emitter voltage. Now, quiescent collector emitter voltage, when nothing's happening, is sitting at 3.4 volts for this particular setup, for this bias. As you increase the base current, that collector emitter voltage drops. And as you decrease the base current, the collector emitter voltage goes up. Keep in mind these 2 points, right here at the top of the load line and down here at the bottom of the load line. At the very bottom of the load line, what is that called? That's called cutoff. VCE equals VCC, equals your power supply voltage, because there's no current going through it. On the other end, when it's fully on, which is actually right over in this area here, you have the minimum amount of VCE and the greatest amount of current. Those are two very important points. See if I can get my, there we go. Yeah, the base current is 300 microamps. Input causes the base current to vary between 200 and 400. Collector current varies from 20 to 40. Now, if you go too far, all right, in other words, if your base current is too high, what happens is you go beyond cutoff, or, and this doesn't show it here, but you can go beyond saturation too. So in this case, this shows this input signal going up and down. That's your base current. And it goes a little bit too far, so it goes beyond cutoff. So one of the most common ways of biasing a transistor, and this is what we focus on a lot, is to do a voltage divider. You just kind of put the base at its VBEQ, quiescent base voltage, okay? And you do it with a voltage divider, very simple, two resistors going to VCC. We also have a collector resistor and an emitter resistor. These are all very important for the correct operation of the amplifier. So it's a simple voltage divider. We have VB equals R1 divided by R1 plus R2 times VCC. That's what that base voltage is, right? So if we have 27K and 12K, simple voltage divider results in 4.62 volts right here. Now this ignores the base current, all right? There's another branch here that is, it's a small current though, it's microamps, whereas if this is called, these are smaller resistors, in other words, they're not 100K or 1 mega ohm, it's called a stiff voltage divider, all right? Meaning that the currents associated in this branch of the voltage divider kind of outswamp the base current. So it doesn't come into play. That said, we actually do some calculations later on which Theveninizes those resistors and takes it into account. So we have 4.62 volts here on the base. We'll do that in a minute. It was 4.62 volts on the base as a result of that equation or that calculation. And so what's VE? Here's the emitter. Well, remember, when a transistor is operating, and we're assuming it's in quiescent, it's just sitting here operating. This is a diode. This VBE is a diode. So 4.62 minus 1 diode drop, that's 0.7 volts, you end up with 3.92 volts. So if you have 3.92 volts here at the emitter, what can you calculate? Well, you can calculate the emitter current, right? And that's what this is. Emitter current, 3.92 divided by 680 ohms is 5.76 milliamps. So this is, as I was saying, we assumed it was an unloaded voltage divider. In other words, no base current. But you can Theveninize these resistors and come up with something a little bit more accurate, and that's what this treatment does. The Thevenin equivalent of is 8.31K, and you can just put that in series with the 4.62, and you end up with a 8.31K resistor as the Thevenin equivalent. And then you can do a little bit better calculation, a little more accurate calculation of that, where we're sitting at here with this bias voltage. So we can write KVL around the base emitter circuit and solve. So we got 4.62 volts here. We have a current through resistor. We've got 0.7 volts here. And we've got the resultant emitter current. And that's what this equation is, the KVL around that loop. So the emitter current is the Thevenin voltage minus VBE, which is 0.7 volts, divided by the emitter resistor plus the Thevenin resistance divided by beta DC. Okay. Now, beta DC, you have to take that into account, right? Because we know that this current, the emitter current, is going to be, in this case, 200 times greater than this base current, okay? So as a result, okay, what we do here is we take the Thevenin equivalent resistance and we divide it by 200 because it's effectively 200 times less because of this current gain. And we just substitute that and solve. We end up with a emitter current of 5.43 milliamps this time, and emitter voltage of 3.69 volts. So that's a little different than what we had before. Still pretty close, and quite honestly, most of the time when we do this in practice, in the real world, we do it just the simple voltage divider method to make sure it's a stiff voltage divider. Okay, so we don't have to worry too much about the base current. And you can obviously check it with multi-sim. So we can do this with a PNP transistor. Okay, we've been looking at NPN transistors, but you can do it with a PNP transistor. You just flip everything around and reverse the voltage. So up here we have minus VEE, so this is a negative voltage at the collector. All the currents go the opposite way. So current comes out of the base, goes into the emitter, right? And then out of the collector, back into VEE through RC. You can also use a positive supply and supply it to the emitter circuit. Just flip everything around. It's the same basic thing, as is this. This is, the B and C are the same thing. They're just mirrored. Okay, if you take all the whole circuit, flip it on its end. And there's a little example here. We're going to assume a stiff voltage divider, so we're not going to do the Thevenin. So we get 10.4 volts using the same technique, voltage divider. Okay, and we can calculate VE by adding this 0.7 volts. Remember, you have to add it. You can't subtract it here because it's going the other way. Cathode is on the base side. So you get 11.1 volts on the emitter. And emitter current is 15 volts minus that emitter voltage. Divided by 680, you get 5.74 milliamps. There's a couple other kinds of bias. Now that was a voltage divider bias, which is honestly the most common way of doing these things, these amplifiers. But there's a few other bias methods that come up every once in a while, and sometimes you're looking at a schematic and you go, well, what the heck is this? You know, I don't remember seeing this kind of bias circuit before, because I'm so used to looking at voltage divider bias. That's what I always look at. But indeed, they do come along at times, and then emitter bias is one of them. But that does require a positive and negative supply. A lot of analog circuits have emitter bias. So we have an NPN transistor here, and we're going to assume -1 volt here on the emitter. And if you assume that, what's the current? Well, it's, again, simply Ohm's law. It's going to be 14 volts across this emitter resistor of 7.5, right? And you end up with -1.87 milliamps. And you can, multisim's pretty close, right? 1.805. And you can include the effective beta DC if you want to. That's probably what they're doing in multisim. That's why our calculation was off a little bit. Now there's also base bias. Now base bias is not really common in linear applications. It's mostly for switching circuits. In other words, the transistor going from completely saturated to completely cut off. So that'd be on and off. So the base current's derived from the collector supply through a large base resistor. IB is going to be 0.7 volts, right? Because the emitter is grounded. So the base voltage is what? 0 plus 0.7. So we're going to go 15 minus 0.7 divided by the 560K, and you end up with 25.5 microamps. Not real common. Don't see this very often, this base bias thing. And we can calculate VCE for 2 different cases of beta. beta is 100, multiply the base current times that 100 to get 2.5 milliamps roughly. And then for, there's VCE, 10.4 volts. And then for the beta of 300, you're going to get 7.65 milliamps. Okay. And a smaller VCE. What might be interesting here is the nonlinearity. Notice that we're tripling beta, which would make you think that, well, the collector current should go up by 3. So you just take 2.55 times 3. I'm not so sure that's what this works out to be. Maybe it does. I don't know. Usually it's not very linear. Okay. And now there's an emitter feedback bias. Now, emitter feedback bias is similar to the base bias, except it adds this emitter resistor. And they say in the notes here that it's a negative feedback. Why do you think that's negative feedback? Negative feedback is something that when you move something in the positive direction, there's a feedback element that pushes it back to the negative direction. In other words, it compensates for it. Why does that work in this circuit? Well, look at this. If you have greater current going through your collector-emitter junction, in other words, collector current increases, therefore emitter current increases, what happens? Well, you induce a drop of voltage across RE. As that voltage increases, what happens? The VB decreases, right? The difference between VCC and VB decreases as this point, the emitter goes up. Because this is a 0.7 volt. The VB is 0.7 volts always. So as the emitter voltage gets higher, because of this increased current going through the emitter resistor, what happens is it compensates with what it causes is the base voltage increases, and therefore the difference between VCC and VB is less, and therefore the base current is less, thereby reducing the collector current and emitter current. So it balances itself out. Does that make sense? So that's why the negative feedback property is happening here. And in fact, when we get further on, we'll see that all of the voltage divider bias amplifiers that we do have an emitter resistor in here for that very reason. Okay, and it prevents something called thermal runaway, which we'll get into later in a different chapter. So again, they do the same KVL equation. Okay, on that, there's no difference, it's the same. And finally, we have collector feedback, uses another form of negative feedback. Okay, but again, as you increase this collector current here, this voltage decreases, and so therefore, because you have more voltage drop across RC, so therefore you have less voltage right here at this collector node, which produces less current through RB feeding the base. So it's a similar setup, but that's called collector feedback bias. Don't see a whole lot of those either. And there's another KVL equation for that. And we do a little comparison here, beta 100 and beta 300. This one's clearly not linear. It goes from 2.8 milliamps to less than 5 milliamps when we increase the beta by 3. So it's very nonlinear. Okay, here's some key terms. Q point, DC load line, linear region, stiff voltage divider, and feedback. Let's go over a couple of those. Q point is a DC operating point of an amplifier specified by voltage and current values. So that's the point that it sits at when there's no input stimulus. So it's silence in the microphone, for example. It's just sitting there. And our load line is the straight line plot of IC and VCE for a transistor circuit. You climb up and down that load line. How? By changing your base current. Linear region is the region of the load line between saturation and cutoff. As soon as you get towards saturation and cutoff, your sine wave starts flattening out. That's called clipping, you know. And unless you're a guitar, electric guitar musician with a fuzz pedal, you don't want clipping. Now, if you play the electric guitar and you have a fuzz pedal, that's exactly what's going on. Is they're saturating the input, and you're getting a lot of squaring off of the sine waves and a lot of what's called odd harmonics, and that's what that fuzz sound on the guitar is for a fuzz pedal. And a stiff voltage divider is a voltage divider on the voltage divider bias amplifier where the resistors are low enough value that there's enough current going through the voltage divider that it does not compete, or the base current will not compete with it. So the base current's in the microamps, your voltage divider currents are well into the milliamps, okay? And then feedback is returns a portion of the circuit's output back to the input, usually as a voltage, to oppose or aid a change in the output. Now, if it opposes it, it's called negative feedback. If it aids it, it's positive feedback. Okay, we do use positive feedback in some circuits, primarily oscillators, which we talk about later. Okay, so that's it for today. And good luck, everybody. If you have any questions, please pose them to the discussion section of our Canvas site. Okay?